Is everybody able to see my screen? Okay, awesome. Okay, so yeah, like Natasha said, I'm Willow. I'll be presenting today on my senior thesis work. So the title of my talk is Generative Adversarial Networks for Pan Sharpening Thermal Satellite Imagery. And my two advisors on this project have been Natasha and Prof. Donaldson-Matashi at Harvey Mudd. So just a little bit of outline for this project. First, I'll talk about the background motivation behind it, and then go into how I developed a thermal optical patch pair data set. I'll talk a little bit about how I chose the GAN architectures that I did, briefly go over some results, and then discussion and conclusions and some sort of future directions for this work. So first, for the background, I wanted to talk about why high spatial resolution thermal imagery is important. So although like the native 70-meter resolution of current satellite thermal imagery from ecostress is sufficient for studies of large agricultural regions, it does not have a high enough spatial resolution to be fully effective in cities. So on the left, we see high resolution optical base imagery. In the middle, there's the 70-meter native ecostress imagery. And on the right, there's ecostress imagery sharpened to 30 meters. So you can see in the sharpened image that there's irrigated golf courses shown in cooler blue colors than the native vegetation in orange. And then there's also outlines of hotter major roadways in dark red. So this is in Los Angeles, where urban environments are very heterogeneous, making high spatial resolution thermal imagery incredibly valuable for studying urban heat islands, urban carbon cycle science, and just more generally, the impacts of climate change in urban areas. However, even this 30-meter spatial resolution is not high enough for some applications. So why is it important? There's a need to better quantify the urban heat island effect, first for human health purposes, but also for understanding urban ecosystem services, better understanding urban planning and land management practices that will be more sustainable in a changing climate. In addition, the increased urban heat is likely to influence the range and ability to thrive of many species of flora and fauna, but there's a lack of research into the ecological effects of urban heat islands. So I'm hoping that this high resolution imagery can help these studies. And lastly, pre-existing studies focus largely on individual cities, but there's a need to elucidate broader trends and changes of biodiversity and urban heat in a changing climate across more cities. So I wanted to develop a methodology that hopefully is transferable across urban areas and is not specific to one city, for example. And so one way that I thought to do this was using Pan Sharpening. So I wanted to just briefly introduce what Pan Sharpening is in case you're not familiar with it. So Pan Sharpening aims to generate a synthetic high-resolution multispectral image from a low-resolution multispectral image that is a plausible reconstruction of the high spatial resolution features with the addition of multispectral features. So the model takes in an input of a high-resolution panchromatic image, like a black and white image, and a low-resolution multispectral image, and it outputs a sharpened multispectral image. So that has both the spectral features of like an RGB image, but the spatial features and sharpness of that original high-resolution panchromatic image. So ideally, when you're validating this pan sharpening algorithm, you have a pan sharpened image from your algorithm, and you also have a ground truth high resolution multispectral image, and you should be able to compare against those. And I'll talk a little bit later on about why this is important, because for my project, I don't actually have a ground truth image to compare against. Okay, so next I wanted to introduce what a generative adversarial network, or a GAN, is. So GANs take in random noise and also real samples, and they have a generator and discriminator process to generate fake samples that can sort of fool the discriminator. So there's an analogy from the original paper of GANs, and it says the generative model can be thought of as analogous to a team of counterfeiters trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect counterfeit currency. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from the genuine articles. So if you apply GANs to imagery, The generative model is attempting to generate images that are so realistic that the discriminator is unable to distinguish between the legitimate and synthetic images. So I chose to investigate applying a GAN-based framework to the problem of pan-sharpening thermal imagery. So while prior pan-sharpening papers have focused primarily on sharpening multispectral optical imagery with panchromatic imagery, there's only one published study that I know of that's focused on pan-sharpening thermal imagery. And this paper relied on traditional approaches for pan-sharpening, and so just like mathematical and simple algorithmic approaches. And these rely on many physical assumptions that may not hold for satellite imagery, which leads to spatially or spectrally distorted and inaccurate super resolved products. So in the last few years, several papers have been published that focus on pan-sharpening with GANs. And although GANs require a large amount of training data and can be time consuming to train, both of which I'll talk about later, they have been shown to generate more realistic pan-sharpened images and are less prone to overfitting than traditional approaches. So the two research questions that I wanted to talk about this today are: first, can a GAN-based pan-sharpening model trained on RGB and panchromatic imagery be used to pan-sharpen thermal and RGB imagery? And secondly, does a pan-sharpening model trained only on thermal and RGB imagery produce higher quality results than the first? Okay, next I'm going to talk about developing a thermal optical patch pair dataset, which took up most of the first semester of my thesis project. So I based my methodology off of the CENI 1-2 patch pair dataset. And this is a pre-existing published data set of remotely sensed imagery, and it contains over 280,000 patch pairs of spatiotemporally co-located Sentinel-1 SAR and Sentinel-2 optical imagery patches to support novel deep learning approaches, including image-to-image translation between SAR and optical imagery. So in this thesis, the patch pair approach to generating a training data set of co-located images will be extended to my satellite data sources of thermal and optical imagery. So I largely followed the same steps as the flowchart on the top, randomly sampling ROIs, mosaicing the images, manually inspecting them, tiling them, another inspection, and then exporting as image patches. And I'll go into my steps more in detail. And at the bottom, there's some example patch pairs. We see that the top row is SAR and the bottom row is optical imagery. And those are pretty closely linked in time and exactly located in space. So in order to develop a pan-sharpening methodology that theoretically could be generalizable to cities with varied urban environments rather than a model that is overfitted or specific to a single city, I obtained training data from 5 different cities. So the thermal optical patch pair library is geographically constrained to target urban areas of Los Angeles, Austin, Boulder, Chicago, and Washington, DC. These cities were selected to represent a range of urban environmental types, including cities with differing population densities, climate classifications, and urban-suburban dynamics, and of course are located across the US. So the 2 types of imagery that I used for my thesis project were PlanetScope RGB imagery and EcoStress LST imagery. So that would be the thermal imagery. So RGB imagery from PlanetScope is taken from a constellation of 130 Earth-observing satellites operated by Planet. These cover the entire Earth every day with 3-meter spatial resolution. And the most recent PlanetScope satellites, the SuperDoves, have been calibrated with Sentinel-2 optical imagery and generally have fewer image quality issues than earlier Planet satellites. And I'm a participant in Planet's education and research program, so I was able to access this imagery for free. So anybody who's in an academic institution can access this imagery. And on the right, there's EcoStress imagery, which has been actively collecting data since July 2018 and measures thermal infrared radiation. So the precessing orbit of EcoStress on the International Space Station means that it leads to sporadic spatial and temporal sampling with revisit frequencies varying between 3 to 5 days, depending on latitude and acquisition times. And so the focus of this thesis will be on the level 2 EcoStress LST product, which has a spatial resolution of 70 meters. And so I gathered both EcoStress and Planet data from all 5 of my target cities for 4 different seasons. And I got cloud-free imagery as well. And planet imagery tiles are 25 square kilometers, so they have a substantially smaller swath width than eco-stress imagery tiles. So it's necessary to mosaic together multiple planet tiles for each target city and season to cover the entire study area. So here is Washington, DC. You can see that within an eco-stress tile, it's very small. So here's what one of those 2 kilometer ROIs, region of interests, look like. So on the left is the high resolution multispectral RGB image. You can see there's sort of a golf course with some development in the middle. And on the right is the co-located LST image. You can see that the temperatures are generally hotter where there is development as expected and cooler where there is more vegetation. So each city has between 9 and 22 kilometer ROIs, and each of these ROIs has imagery from 4 seasons. So the next step was to split each of these 2 kilometer ROIs into non-overlapping 128 by 128 pixel patches. And then each patch was saved as its own unique georeference TIFF file. So the 128 pixel patch size is based on RGB imagery. So each pixel is assumed to be 3 meters in spatial resolution. So you can see zoomed in the middle here, that includes 428 by 128 patch pairs of the PlanetScope imagery. So there are around 16,000 3-meter planet pixels in one 128 patch pair, whereas on the far right, there's only around 30 ecostress 70-meter pixels in a single patch pair. So after tiling was completed, there were roughly 6,800 unique thermal optical patch pairs across all 5 target cities and in different seasons. So after the tiling was completed, all patch pairs were manually inspected by me, and any patch pairs with snow contamination or cloud contamination were removed from the data set. So for example, pretty much all of the Boulder winter imagery was contaminated with snow, so there is no Boulder winter imagery in this data set. And although I tried to obtain cloud-free images from Planet's API and EcoStress's online search, there's still some clouds that weren't caught, so it was necessary to go back through and look for all of them. Okay, so next I'm going to talk about the GAN methodology. So the first GAN framework that I looked at was Pan Color GAN, and it treats pan sharpening as a colorization problem rather than traditional pan sharpening methods that aim specifically just to generate a high resolution version of a lower resolution multispectral image. So one motivation for this change is that using a GAN-based colorization approach helps to avoid spatial detail loss and blurring that can occur with traditional pan sharpening algorithms. So here's a proposed scheme from the Pan Color GAN paper. It converts a high resolution multispectral image to grayscale, and then it also downsamples it to create a low resolution multispectral image, feeds both of these into a generator, and theoretically can generate a high resolution multispectral approach that is a good representation of the original multispectral image. And it does this through 2 types of losses. So there's a reconstruction loss that increases pixel-wise similarity between the generated image and the original multispectral image, and the adversarial loss that narrows the distribution between the generated images and the multispectral images. So this adversarial loss is where the adversarial part of GANs comes in, and that's making those fake images look more like the real image. So all of these images were, both the panchromatic and the downsampled were from the same satellite platform. So this isn't super realistic for thermal imagery or for my project because EcoStress and PlanetScope are on completely different platforms. So that's just something to keep in mind going forward. So the Pan Color GAN framework was used to address the first question, where I was testing the applicability of a pre-trained GAN model that was trained on RGB panchromatic patch pairs from a different data set to the novel problem of thermal optical pan sharpening. So I have my thermal optical patch pairs. They were normalized from -1 to 1, then fed into the pre-trained Pan Color GAN model, which then outputted a pan sharpened image. I applied Gaussian smoothing, which I'll talk about why that was necessary, and then denormalized it back to Kelvin. So I'll talk a little bit more about the results and what this looks like later, but I wanted to first show that the normalized LST and the normalized RGB images are fed into the pre-trained model. The pre-trained model then outputs something that should be pan-sharpened LST. Okay, so the other pan sharpening framework that I used is Pix2Pix, which is an image-to-image translation algorithm. And this means that it learns the mapping from an input image in one domain to an output image in another domain. Traditional algorithms for image-to-image translation were very application-specific, which made it difficult to replicate the same approach on different problems. However, the Pix2Pix GAN algorithm changed this by using a standard conditional GAN architecture that can be generalized to many disparate image-to-image translation problems. So this is from the original Pix2Pix paper in 2016, and you can see that there's a lot of different problems, colorization, going from day to night. There's even evidence that Pix2Pix was developed to work with satellite imagery, given the aerial to map case that was given on the bottom left. So the Pix2Pix framework was used to test the feasibility of training a new GAN model for pan sharpening using only my thermal optical patch pair data set. So the first thing to do was splitting my data set into 80% training and 20% testing patch pairs. The training patch pairs were then normalized again from -1 to 1. I applied data augmentation since my training data set was relatively small. Then trained a Pix2Pix model, and then the testing patch pairs were then fed into this trained Pix2Pix model, which then output pan-sharpened imagery, and then it could be denormalized to Kelvin. So again, I'll talk more about what these results look like later, but the Pix2Pix architecture was allowed to train on the novel thermal optical patch pair dataset for 30,000 epochs, starting from a 128 square pixel image of randomly generated noise on the top bar. And then after training was complete, after epoch 30,000, the network was then applied to previously unseen thermal optical patch pairs. Okay, so next I'm going to talk about what the results of pan sharpening looked like from both frameworks. So first, from pan-color GAN, the pan-sharpened images that were synthesized by the pre-trained pan-color GAN network appeared to maintain many of the high-resolution spatial features from the ground truth RGB images. However, the resulting pan-sharpened images also contained edge artifacts along the borders of the LST pixels, which are not representative of the spatial features of the ground truth RGB image. So this is not entirely surprising, given that the temperature between subsequent LST pixels is likely to vary and could lead to spectral differences between 70-meter LST pixels. However, it doesn't look great in the result. This obviously isn't super representative of ground truth if we had any. So to address this issue, Gaussian smoothing was applied to minimize the visual appearance of edge effects while maintaining the improved spatial resolution of the sharpened image as much as possible. So here is what Gaussian smoothing looked like. So applying a Gaussian smoothing filter can reduce image noise and give the appearance of what looks like a smoother image by giving less weight to pixels located further away from the center of the Gaussian kernel. And this is particularly valuable for smoothing edge effects because the pixels furthest from the kernel center are those that contain edge artifacts. So what determines the blur quality of Gaussian smoothing is the sigma value. So higher values of sigma correspond to a blur effect, whereas the upper left-hand, where there's no smoothing, that's a sigma of 0 and no blurring is applied. One challenge of Gaussian smoothing is determining which is the most appropriate sigma value that minimizes the visual appearance of edge effects while also maintaining the improved spatial resolution of the sharpened image. Just from a visual inspection of a bunch of different sharpened patch pairs, I chose the sigma value of 4, which is highlighted in red. That seemed to be the best balance to me. And so once Gaussian smoothing was applied to the pan-sharpened LST image, it got rid of those odd edge effects in the pan-sharpened LST product and produced something that you're able to still see the outlines of a city block. You've definitely gained spatial information over the LST-only image and lost those edge effects that are distinguishing the edge of a 70-meter pixel. And this is using a sigma value of 4, again, for Gaussian smoothing. So here are the results of the Pix2Pix network, and this was trained only using the thermal optical patch pairs. So the pan-sharpened thermal images that were synthesized from the Pix2Pix network did not adequately maintain the high-resolution spatial features from the RGB image or the spectral features from the corresponding LST image. You can see that it sort of produced something that kind of looks a little bit like RGB colorization, even though it should be an LST image. So the pan-sharpened images appeared largely indistinguishable from one another, regardless of what inputs you gave them, and they have repeated grid-like features that were not representative of the ground truth data. And I'll talk a little bit more about why I think these appeared in the discussion section. So since there was no real ground truth data, I didn't have any high resolution thermal imagery to compare my results against. I validated and checked the results of my pan sharpening algorithm with image quality metrics. And these metrics measured both the spectral and spatial distortion of the image. So spectral distortion is trying to answer the question, how spectrally similar is the pan sharpened image to the original LST image? Whereas spatial distortion is trying to answer how spatially similar is the pan sharpened image to the RGB image. Ideally, the pan sharpening algorithm should produce an output that has minimal spectral distortion to preserve the LST values and minimal spatial distortion to preserve the spatial features of the original high resolution RGB image. So one of the image quality metrics that I used was RMSE, and it's used to measure either the spatial or spectral distortion of a pan sharpened image against the ground truth RGB or LST image respectively. For both pan-color GAN and pix-to-pix, spectral distortion is higher than spatial distortion, which suggests that pan-sharpening thermal imagery preserved the high-resolution spatial features better than the spectral information, which was confirmed by my visual checks as well. And when comparing the distributions of RMSE between pan-color GAN and pix-to-pix, the spectral and spatial RMSE of images sharpened with pix-to-pix are higher than those sharpened with pan-color GAN, which indicates that pan-color GAN produces less distorted pan-sharpened thermal images, which again lines up with my visual checks. And the other image quality metric that I chose to focus on today was ERGAS, which shows the quality of a sharpened image. Similar results to RMSE were found for ERGAS, which measures the spatial or spectral quality against the ground truth RGB or LST imagery respectively. Again, for both pan-color GAN and pix-to-pix, spatial quality was higher than spectral quality. And when comparing the two sharpening algorithms to each other, the spatial and spectral quality of images sharpened with pix-to-pix was lower than those sharpened with pan-color GAN. So pan-color GAN produced higher quality sharpened thermal images. So both image quality metrics sort of lined up with each other and agreed with the visual checks that I made. So next I'll talk a little bit about the discussions and some areas for future work. So the first question that really came up was, is the sharpened product actually thermal imagery? This is an output from the pan-color GAN image sharpening algorithm. So the units of RGB are in intensity. When the LST image is denormalized, it's in Kelvin. When the pan-sharpened LST is denormalized, it theoretically should also be in Kelvin. So the main issue for this thesis was that the pan-sharpened thermal imagery did not quite have the correct range of Kelvin to correspond to the thermal imagery after denormalization. The range of values was generally close to the expected values, but it was much smaller than it should have been. So in this figure, the expected range of LST was around 304 to 311 Kelvin, but the pan-sharpened image only had a range of 312.8 to 312.9 Kelvin. So it's outside the range of expected values, and it's got a very small range in variability, but you can see that it maintained the spatial features of the high resolution RGB image. So one reason for this discrepancy in units may be the method by which LST images were normalized during patch pair creation. So each LST image was locally normalized between 0 and 255, and then the local minimum and maximum values in each patch pair were recorded for denormalization after pan sharpening. And local normalization was necessary in order to retain as much information about LST as possible within a patch pair, but it also meant that normalized temperature values were not directly comparable between patch pairs. And I think this may be a reason why it's not producing true thermal temperature values. And the issue of incorrect images on a final product while performing image-to-image translation has appeared in previously published studies. For example, there was one that attempted to convert between SAR and optical satellite imagery, and the authors hypothesized that it wasn't possible to fully convert between imagery types, So it generated a product that's sort of halfway between SAR and optical imagery. And that's another thing that could be happening here. Another thing that another reason why the pan-sharpened images produced by the pix-to-pix model may not have looked so great when they were trained only using the thermal optical patch pair data set is that the number of patch pairs was probably too low to train a high quality GAN pan-sharpening network. So my thermal optical patch pair data set contained around 6,788 images. But the other published GAN architectures used 35,000 images, 50,000 images. And so this is substantially fewer training and test images than other published algorithms. Like I mentioned at the start of this presentation, GAN models are notorious for requiring large training data sets in order to produce realistic images. So it's not super surprising that the small size of my thermal optical patch pair data set limited the quality of the pix-to-pix pan-sharpened thermal imagery. So in order to constrain the scope of this project to a senior thesis that could be completed in one academic year, the number of target cities was limited to 5, which is part of why the number of patch pairs is so low. In addition, manually inspecting each of the thermal optical patch pairs to ensure they didn't contain clouds or any other visual aberrations was time consuming. And it was necessary, to make sure that no extra clouds got in. So this methodology could be extended to other cities, which just would require more time, but I think that it could most certainly produce higher quality GAN networks if it was trained on more data. So the other issue is that there was a lack of ground truth high resolution thermal imagery. In an ideal world, there would be a data set of simultaneously acquired high resolution and low resolution thermal satellite imagery so that there's a true ground truth image. So for example, we could have RGB imagery and LST imagery that were fed into the Pansharpening algorithm. It would output pan-sharpened LST, and then I would also have a ground truth high resolution LST image to compare against. However, this doesn't exist. So given these limitations, it's necessary to compare the spatial resolution in the pan-sharpened image against the RGB image and compare spectral information against the LST image. There's also potential for comparing against other high resolution LST maps and sharpening algorithms once those are published. So yeah, that was definitely a major barrier, is the lack of ground truth validation. So another GAN pan-sharpening algorithm that looks particularly promising for pan-sharpening thermal imagery using weights that were trained on the thermal optical patch pair dataset is PanGAN. I spent a little bit of time trying to implement this algorithm, but ultimately ran into challenges and ran out of time to complete within my senior thesis. But I do think that it's a very promising architecture. So the PanGAN network architecture was designed specifically for pan-sharpening remotely sensed imagery. And it has 2 discriminators, one that is used for preserving spectral content and the other that is used for preserving spatial content. So these discriminators are independently trained. And I feel that this could help with the issue experienced in my thesis, where spatial content was preserved more effectively than spectral content. I think if there was a second discriminator that was solely focused on preserving spectral information, this could reduce some of the distortions that I experienced. Okay, so lastly, the conclusions of my thesis. Returning to the original research questions, can a GAN-based pan-sharpening model trained on RGB and panchromatic imagery be used to pan-sharpen thermal and RGB imagery? And then secondly, does a pan-sharpening model trained only on thermal and RGB imagery produce higher quality results than one? So to answer that first question, I found that yes, a pan-sharpening model trained on RGB and panchromatic imagery can be used to pan-sharpen my thermal optical patch pair dataset, but the resulting image retains more of the spatial features from the RGB image than spectral features from the LST image. In addition, Gaussian smoothing was necessary to reduce the edge effects, and the resulting temperature units are not fully correct. So to answer question 2, does a pan-sharpening model trained on thermal and RGB imagery produce higher quality results than a pre-trained model? And I found that this was not true in my case. I feel that the thermal optical patch pair dataset was likely too small to train a GAN that can produce realistic results. The pan-sharpened images out of Pix2Pix were indistinguishable from each other and had unrealistic repeated grid-like effects, and the units of temperature were not correct. So overall, I found that pan-color GAN with pre-trained weights produced higher quality pan-sharpened images than Pix2Pix that was trained only on the thermal optical patch pair data set. This conclusion was based on my visual examination of a lot of sharpened patch pairs and also on the image quality metrics data that I shared. However, I'm not sure that this conclusion will hold with a larger training size. So if Pix2Pix was trained with a more representative and larger thermal optical patch pair data set, I would hypothesize that that would create higher quality results than the pre-trained one, just because it's picking up on more thermal consistencies between images. So ultimately, neither method of pan-sharpening produced true thermal imagery, which is why more work is needed on this to produce realistic results. Found that pan-sharpening successfully recovered many of the spatial details of the high-resolution imagery, but failed to retain some of the spectral information from eco-stressed LST. So perhaps using the pan-GAN architecture that has both that spatial and spectral discriminator to maintain both types of information will be helpful. Lastly, for acknowledgements, I'd like to thank Natasha for all of her guidance and support on this thesis project, and also over the past 3 years of working together, both at JPL and outside. I'd also like to thank Glenn Hulley and Nick Parazu, who supported my initial research into LST and urban heat islands while I was interning at JPL. And lastly, I would like to thank my other thesis advisor at Mudd, Matino Donaldson Matashi, for providing lots of editorial feedback on my thesis and welcoming me into her lab at Mudd. Thank you. Are there any questions?
Ooh, thanks. Feel free to use the reactions to applause. I know that it is really hard in the virtual environment to really truly see and feel praise. So use those reactions liberally. Willow, it may be beneficial to come out of screen sharing mode so that we can see everyone's faces. Yeah. And I see Stefan put a question in the chat. If Stefan, you want to jump us off on discussion, and then I will just ask that people, for those who aren't familiar with Zoom, at the bottom of your screen, there's a reactions with a smiley face and there's a raise hand feature. So go ahead and raise your hand when Stefan's done. We'll work through the line. Okay, Stefan, take it away.
Okay, thanks for the talk, very interesting. I have a few questions. I put them in the chat, but I can also just repeat them one after each other. So I think right at the beginning, you talked about using planet scope data, which only has 3 channels. And I was just wondering why you chose to use planet scope data rather than anything else.
Yeah, absolutely. So I chose to use PlanetScope data mostly because it was the highest spatial resolution imagery that I had access to for free. And I also interned at Planet last summer, so I had experience working with that imagery. I've worked with Sentinel before, and I know that Sentinel has sort of better calibrated, image quality metrics in some senses, but I wanted to try it out with a different type of imagery. My methodology for developing the patch pair data set could certainly be replicated with Sentinel 2, for example. And when I first started this thesis, I actually was planning on using both, but then decided just to stick with PlanetScope for simplicity.
Okay. And then I was wondering whether you checked, so you said at the end that maybe if you had more training data, this would solve some of your problems. And I was just wondering whether you did some ablation studies where you probed for that.
Yeah, not super formally. I did try, I trained it once just using the patch pair data set. So 4,000, I guess, or 5,000. And then once where it was augmented. So that doubled the amount. But it was doubled with, augmented imagery. So it was just jittered or rotated. And I think because that, was not quite a true ablation study and was using the same type of data, I didn't really get any different results. But yeah, that would be a interesting idea.
Then I was also wondering, so I didn't quite understand. So you don't have ground truth, which prohibits you to really say which model is better. And you try to use some RMSE and just calculations. And I didn't quite understand how you calculated them and how like how much I can trust them and look at them and say, oh yeah, one is really better than the other one. Maybe you can just explain that again.
Yeah, absolutely. So I agree, there's not ground truth, so it's not super quantifiable which one is truly better. But the way that I did it was, so if it was measuring the type of spectral distortion, I was comparing the pan sharpened image only against the RGB image. Or sorry, spectral was pan sharpened image against the LST. So that was sort of measuring like the variability between only the spectral features. Whereas for the spatial one, I was comparing the pan sharpened image only to the RGB. And I was just using the like a built-in RMSE function from Python and some other studies that I'd seen test like pan sharpening algorithms had used those as well. One thing that I had also thought of for measuring like the spatial quality was potentially comparing it against like the Microsoft OpenStreetMap like building outlines, just to see how well it was picking up on the spatial features. But since I sort of realized that the quality of these images wasn't quite right anyways, as far as like spectral distortion, I didn't end up going that route.
Okay. And then my last question was just that on slide 21, you showed how pix-to-pix can like be used for a variety of problems. And like there was, for example, in the bottom right, there was a picture of a handbag where they were just like the outlines, and then the pix-to-pix filled in the color without having any knowledge of what that color should be. So it basically just hallucinated a solution for this image. And I'm just, when I hear people using GANs for earth science applications, I just get worried that we get solutions that look very realistic because that's what the GAN is trying to do, but they could be completely wrong. But you look at them and you say that looks good, like it's a high quality pan sharpened land surface temperature. Like, did you try to investigate somehow whether you had some kind of hallucinations going on where, for example, you would take away some of the information or anything in that direction, like where you just see whether you can trust the results of your GAN?
Yeah, that's definitely something that I also talked about more in my written thesis as well. And I'll publish that and can share the information as well. There's been some really interesting studies published in the past like year or so about like the ethics of using GAN specifically on satellite imagery. So that's something that I was concerned about as well. For the pix-to-pix one, where it was like generating bad results, it was most clearly hallucinating something there. So that is something that I was worried about. And I'm not sure that I have a good solution. I'm not sure that I would fully trust these results either, even if they were more accurate. It was kind of more of an interesting study of like, can this be used? Obviously, like we're relying on this as ground truth imagery for something where it could be really impactful or like, ethically dangerous. There were some like in one of the papers I read, there were like concerns about like, for example, like planning like humanitarian escapes. If somebody used like synthesized imagery and there was no bridge there, that could be really problematic. So I think there definitely needs to be more research into GANs. And that was something that I was thinking about from the start of when I proposed this thesis.
Okay.
Oh, this is cool, but it's a little scary as well.
Great. Thanks a lot.
Teo, I think you were next, and then Endong, you're next.
Hello. Thank you for the talk. Very enjoyable. I guess I have a couple related questions. First is sort of a clarification question. I apologize if this is harping on the same question, but this question of ground truth. So just to clarify, so I guess two sort of clarifications. First is that there just isn't ground truth of this type, period, in the sense like there isn't a satellite data set of high resolution thermal imagery. Is that correct?
Yeah, not that I have access to. I was trying to largely use open source data set. I think there might be like some commercial thermal satellites that are like starting to come on in like the next few years, but no, this was not available.
And so for the in this like GAN framework, when we're passing the synthesized images to the discriminator, and then I guess my understanding is usually we'd also be passing samples from like a real data set. I might have missed, where are those samples coming from then if we don't have access to this like high resolution data set?
Yeah, so it's for the pix to pix one. So for the one that was treating it as a colorization problem, the like diagram that I showed where it was like feeding in the models, since for that one, I was just using the pre-trained weights. I didn't need ground truth because there was no training occurring.
Okay,
and then,
gotcha.
Yeah, so for the pix to pix one, it was image to image translation. So it also doesn't require that ground truth as much because you're just sort of like mashing the two of them together. However, if I ended up using the like Pan Gan one, that one also that one works better with a high resolution ground truth, but it doesn't require it. They like tested it in both ways. So I tried to pick GAN frameworks that did not require that ground truth now. So sorry if that was not clarified before.
No, yeah. I think I maybe just like misunderstood as doing some transfer learning.
Yeah.
Versus like just like using that as the set of training weights. Okay, so I guess based on that, I'm wondering maybe if you have any thoughts on this. You know, and maybe it's a fool's errand to try to like hypothesize what these kind of systems are doing, but if there would maybe be any work in like moving up in a scale where you can downsample your RGB or like panchromatic imagery and sort of if we worked at like a lower resolution altogether where we're sort of sharpening to the resolution of the low spectral imagery, do you think that could be transferable to this like high resolution imagery? And I guess that a related question would be like, do we think that these GANs are learning sort of feature specific aspects of the high resolution imagery, like you mentioned, like golf courses or something, or is it more in a purely shape based way that might be transferable across resolution scales?
Yeah, so I think part of the issue with that is that so that's the way a lot of these GAN networks are trained, is with like artificial downsampling. But artificial downsampling is like not necessarily representative of how different scales of satellite imagery are like related to each other. So like the way that it's, artificially downsampled using like, nearest neighbor, some sort of like bicubic interpolation. Some like recent studies have shown that that's not like the way that like a lower resolution satellite imagery from like a different platform is related to the high resolution one. So I think there's concern that like it might learn like an upscaling or downscaling method that's not really realistic when you're looking at non-synthetically downscaled images. As far as the like features versus shapes, I'm not really sure. I think especially when you're looking at thermal imagery, it's more complicated because I'm not really sure that I fully understand how it's learning what thermal, which sort of landscape features have thermal classes. So that definitely increasing the transparency of these models is important.
So I do want to, Teo, I want to give Andong a moment to ask their question before we run out of time. So if you have any more questions, feel free to throw them in the chat. But Andong, do you want to ask your question?
Yeah, so can you hear me?
Yep.
Okay, that's great. So thanks for this presentation. So that's very interesting topic. And my questions are, so the first one is, I just want to double check. So what's kind of the LST data you use? I mean, for the last surface data, it could be sent kind of gray level image, which means that it only have one band or the one channel. So I noticed that in your presentation or in your slides, all those LST images are colored. So that means you may give a kind of the color table to make it as kind of 3-channel image. So my first question is, when you use those LST images during the training procedure, so what kind of input you use? You use the 1-channel LST image or the 3-channel ones?
It's a 1-channel LST image. It was just colorized using, for the pictures of it, I just colorized it using like a 1-channel matplotlib image.
Okay,
yeah.
okay, I see that. So that's for the display purpose, right? Okay. And the second question is, so I noticed that during the data preparation slide, you mentioned that you have the star image, I mean the radar image. So did you use the radar image during the training procedure or not?
No, I included that just to show that other authors had produced similar patch pair data sets. I just used the methodology from that paper to create my own training data set.
Okay, so you just use your RGB. Okay, that's
Yep.
And third one may not be a kind of question, but maybe a kind of suggestion. So here is, I noticed that you use the RMSE or another index to evaluate the performance. So did you consider about using some other very popular indices like the PSNR, the peak, signal to noise ratio, or even some kind of the similarity measurements to do it? Because RMSE is a very simple one.
Yeah, I did also calculate like the spectral angle mapper, and I did PSNR as well. I just did not include those in the slideshow. They will probably be in my published thesis.
Okay, yeah, that's good. Yeah, thank you.
So thank you so much, Willow. This was really awesome. I don't see anybody else with their hands up, and I want to be respectful of everyone's time. Willow's thesis will be publicly published through the university, and we can definitely send that around to everybody, which includes GitHub links to some of her code for the work that she's done here. But with that, I think, final round of applause, and thanks, Willow, and thank you everyone for coming